Alright folks, we're joining you here for our second video on section 8.5, finding the area between two curves with respect to y. We're going to pick up right where we left off. We had just finished example 2 on the previous page. Let's look at the beginning here, which kind of talks about some tips. In a lot of cases, in fact, pretty much all the time, we can choose whether we want to find areas by integrating with respect to x or with respect to y. Usually one of the two methods is easier, but sometimes they're both comparably difficult. There are some things that you want to take into consideration when you make the decision of which variable to integrate with respect to. I've got these two numbered bullet, what variable are the equations already solved for? If all the equations are already solved for one variable, that might make it the obvious choice as far as which variable we integrate with respect to. Although sometimes it's easy to solve the equations for the other variable, and we can decide that it might be easier if we just went ahead and did that. Will using one of these methods require multiple integrals while the other one doesn't? Maybe if I use one of them, it just requires one simple integral, and if I do the other, it might require 2 or even 3 integrals. Is it worth it to solve for the other variable in order to use a different integral setup? If I have the equations one way, but it's going to require 3 integrals, what if I solve for the other variable and then it only requires 1 integral? Those are the decisions that you have to weigh when you're doing any of these problems finding area. And we know how to do them both with respect to x and with respect to y, so we can, kind of make our own decisions along the way. Let's look at example 3. We're going to find the area of the shaded region in the graph below, and we're going to do it both with respect to x and with respect to y. Okay, so let's start with respect to x. So if I do this with respect to x, notice that we've got a transition in boundary here. Initially y equals x is the upper boundary, but then at the point 1, 1, the upper boundary changes to the line y equals 1. Meanwhile, the bottom boundary stays the same the whole time. So what that means is I'm going to need 2 separate integrals in order to find the area here with respect to x. I'm going to put a little dividing line down here at 1, and I'm going to find the area to the left of that and the area to the right of that, and add those two together in order to find this area with respect to x. So I've got the integral from 0 to 1 of x minus x squared over 4. That's my first integral with respect to x. And then to the right of my line, it's going to be the integral from 1 to 2. And the upper curve is 1, and the lower curve is x squared over 4. And so there we go. There's our setup with respect to x. Now with respect to y. Let me clear off my picture here. Now with respect to y, all I need to do is go ahead and solve this equation for x. And so I get 4y equals x squared. So x equals plus or minus 2 square root of y. But since this is the right-hand branch of the parabola, it's the positive branch. So I just need the positive branch as my equation for that. All right, now I can set it up with respect to y. I'm going to integrate from the bottom, which is at 0, to the top of the region, which is at 1. And my upper curve is going to be 2 square roots of y, and my lower curve is going to be x equals y. So there's my setup with respect to y. And now I can go ahead and calculate the integrals for both of these and see what the area is. So let's go ahead and we'll calculate the area. This is going to be x squared over 2 minus x to the third over 12, evaluated from 0 to 1, plus x minus x cubed over 12, evaluated from 1 to 2. And so that's going to be 1/2 minus 1/12 minus 0, plus 2 minus 2/3 minus 1 minus 1/12. And we'll go ahead and do the arithmetic on that. And I already did it on my calculator. I get 5/6. I'm going to go ahead and clear off my calculator. Whoa, pause here for a second and clear. Okay, and now I'm going to integrate with respect to y. So we take the antiderivative of this. Let's see, the integral of square root of y is 2/3 y to the 3/2, so that's going to be as such, minus y squared over 2. And we evaluate, that's going to be 4/3 minus 1/2 minus 0, and all of that's equal to 5/6. All right, on to example 4. We're going to find the area of the region bounded by these graphs, both with respect to x and with respect to y. Again, we're going to use our graphing calculator to help us find intersection points, and we're going to use the graph below to help us set things up. All right, so the first thing I'm going to do before I do anything else is I'm going to take each of these lines and I'm going to solve them for x. This is the boundary here is y equals 3/2 x plus 1. If I solve that for x, let's see, that's 2/3 times the quantity x minus x. X equals 2/3 times the quantity y minus 1. That's that boundary. This boundary right here is, let's see, that's y equals 2 minus x squared, so that's x squared equals 2 minus y. So x equals plus or minus, but we only need, this is the positive side of the curve. To the left of the y-axis is the negative side, so we only need the positive branch, x equals positive square root of 2 minus y. And then for this one, I take the square root of both sides, and then I add 1 to both sides. So I've got 1 plus or minus the square root of y, and the right-hand side of this curve is x equals 1 plus the square root of y, and the left-hand side of this curve is x equals 1 minus the square root of y. And we're actually going to need both of them in this because each of those forms part of the boundary of this region. All right, now to find intersection points. Let's go ahead and we'll type our equations into my graphing calculator. So I got y equals 2 minus x squared. Y equals quantity x minus 1 quantity squared. And y equals 3/2 x plus 1. Those are my equations, and my graph here looks like it goes from about 2.5 in each direction, and it looks like that's what I have my window set at. So when I graph this, it should be a pretty good graph for us to see. Here's my one parabola, my other parabola, and my line. So that's a pretty good image of the region. Now I want to find my intersection points, so let's go ahead and do that. We're first going to find where the parabola, bottom parabola hits the line. First curve, second curve, lower bound, upper bound. And so this intersection point is at 0, 1. It's that intersection point right there. And then we'll go for another intersection point. All right, parabola. And this line is the next intersection point that we're interested in. That's at 0.5, 1.75. Right here, 0.5, 1.75. And then one more intersection point. And that's between this curve and this curve. And that's, ooh, an ugly one. We use purple. And that's 1.3660254, comma 0.13394746. Okay, so now we have all the points of intersection. So let's go ahead and set this up. We'll start with respect to x. With respect to x, look at this blue vertical line that divides this into two regions. For the first region, y equals 3/2 x plus 1 is the upper boundary. And the lower boundary is y equals 2 minus, no it's not, it's y equals quantity x minus 1 quantity squared. And that goes from 0 to 0.5. And then we're going to add to that the integral from 0.5 all the way over to this intersection point, which is 1.3660254, 1.3660254. And on that boundary, the upper region is y equals quantity 2 minus x squared. And the lower boundary is y equals quantity x minus 1 quantity squared. Okay, so we've got that set up. And then with respect to y, we're going to go a little bit different here. First off, I need this region down here. And that starts at 0 and goes up to where y is 0.1339746. And on that interval, the upper boundary, or the rightmost boundary, is quantity 1 plus square root of y. And the leftmost boundary is quantity 1 minus square root of y. And then my next region, I've got the integral from 0.1339746. It goes up to here, where y is 1. And the upper boundary is square root of 2 minus y. And the lower boundary is 1 minus the square root of y. And then the last region is going to be the integral from 1 to 1.75. And this time the upper boundary is square root of 2 minus y. And the lower boundary is the quantity 2/3 times y minus 1 dy. And then I can just go ahead and use my numerical integral to find these. I'm going to go ahead and do it with respect to x first. All right, we've got integral of quantity 3/2 x plus 1 minus quantity x minus 1 quantity squared with respect to x from 0 to 0.5 plus integral of 0.5, integral of quantity 2 minus x squared minus the quantity x minus 1 quantity squared with respect to x from 0.5 to 1.3660254. Uh-oh, missing parenthesis. Oops. Where are you, missing parenthesis? Right here. And we get 1.262. Let me check and make sure that I've got my... All right, very good. 1.262 for the area. And now, through the magic of video, I'm going to instantaneously type in all of the curves for y. All right, and now that I have all of that typed in, I'm going to go ahead and hit enter. And see what happens. And lo and behold, we get the exact same area that we did with respect to x. All right, so we can do any of these problems in both ways. You know, sometimes it's, I mean, this one was really difficult with respect to y compared to what it was with respect to x. You know, and so you've kind of got to develop the idea to make the decisions. I don't necessarily always know in advance what the right decision is, but I feel like, you know, as you do more of these, you get into a point where you see that, you know, this is the easiest way to approach this. So it's going to be important for you to do a lot of practice. All right, that takes us to the end of this video and the end of section 8.5. Join us again in the future for section 8.6, where we'll talk a little bit more about finding area between curves. All right, see you then. Have a great day. Bye-bye.